Okay, in section 2.4, we turn our attention to what's called linear functions. And linear functions are any functions that when you graph them, form a straight line. And we know, once again, that a function, when you graph functions by the vertical line test, we can't have any points above other points. So we have linear functions here, here. Horizontal lines would actually be linear functions. But one thing that would not be a linear function is a vertical line, because a vertical line would not be a function. Each and every one of these linear functions, and again, we remind you that a function could start with f of x, which is the exact same thing as y. Any of these linear functions can be written in the form f of x equals mx plus b, which is a very important form that we're going to talk about a lot this section. So let's look at two different relations here, y equals 5x minus 3 and 2x minus 6y equals 7. And talk about whether these are actually linear functions. And again, a linear function is any function that can be expressed in the form f of x or y equals m, and m is going to be some constant, some number. X is going to be an x, plus b, which is also going to be some number. And we notice this first one, y equals 5x minus 3, is already in that form. To where in the place of m, well, there's a 5 there. In the place of plus b, well, we could write this as plus negative 3 if we wanted to. But in the place of b, you actually have a negative 3. So that is a linear function. But the second one doesn't look like it's in that form. But the question is, could we get it in that form? And if we can get it into that form, it's also going to be a linear function. And again, remember that anytime it's a linear function, if we graphed it, we'd have a straight line. We have 2x minus 6y equals 7. And let me remind you of something. Here you have three terms. Terms are separated by plus, minuses, and sometimes equal signs. So 2x minus 6y and 7 are terms. And the way I teach this, the way that you move terms across equal signs, I've told you this once before. To move a term from one side of the equal sign to the other side is extremely easy. All you've got to do, if it's positive, change it to a negative. If it's a negative, change it to a positive. So what we're going to do here is, in order to get y by itself, the first thing I'm going to do is move any term that doesn't contain a y. So I'm going to take 2x and I'm going to put it on the other side. My suggestion, write it first. Notice in this f of x form, my x is first. And then you have some number at the end. So the negative stays, so I now have negative 6y equals 2x turns into a negative 2x. And here's something else you need to know. Since 7 is a positive, there's an understood to be plus sign to be there. So I'm going to write down plus 7. And we're nearly finished. We've nearly got it in this form. Because in the form, all you've got is y is by itself. Then you have your x stuff, and you have your b stuff, your other number stuff. So we've got to somehow get rid of negative 6. Since negative 6 is being multiplied by y, I can remove just the negative 6 and leave the y, since it's being multiplied by dividing by. Now the question is, what do I need to divide by negative 6? I need to divide the entire side by negative 6, both terms. So I'm going to divide my first term by negative 6, and I'm going to divide my second term by negative 6, and it cancels it out. So I now have y equals, and you need to remember your rules for positives and negatives here. Since you have a negative divided by a negative, that will always be a positive. And something else I need to point out is you can't divide 2 divided by 6 without getting a decimal. So what you're looking at doing here is keeping in mind that division and fractions are the exact same thing. Since I can't divide 2 divided by 6 without getting a decimal, we really don't want to put a decimal there. So since I can't divide it, I'm just going to reduce it. 2 over 6 is actually going to reduce to 1/3. Bring down your x. A positive divided by a negative here is going to be a negative. 7, 6 won't divide, it won't reduce, so I'll leave it. So what we've actually done is we've gotten this equation, which we'll learn later on is called, it's in standard form. We've took it from this form and we've written it in the basic form of a linear equation. So in the place of an m, notice I have a 1/3. And in the place of this b out here, I have a negative 7/6. Okay, next up we're going to explore what's special about that m and b. And the first thing I noticed, what I've done here is I've actually graphed 3 different lines. And you can use t-tables to do this. Later on we'll talk about a shortcut way of doing it. But I've graphed y equals 2x plus 5 in red, y equals 2x in pink, and y equals 2x minus 5 in blue. And what I notice here is it looks like pretty much the same line except for just moved up and down. Something else I noticed, there's a relationship between this last number. What was our b term? Because again, all linear functions can be written in the form f of x or y equals mx plus b. And I notice in the place of b here, I have a 5. In the place of b here, I have nothing there. Anytime I have nothing, it's understood to be a 0. In the place of the b here, I have a negative 5. And what I noticed about all three of these equations is if you took and counted up 1, 2, 3, 4, 5, y equals 2x plus 5 crosses the y-axis at 5. Y equals 2x plus 0 crosses the y-axis at 0. And y equals 2x minus 5, 1, 2, 3, 4, 5, crosses the y-axis at negative 5. That, we actually have a term for this. The place where a graph crosses the y-axis is called its y-intercept. So we see from that in this equation, y equals mx plus b, that this b term takes the place of our y-intercept. And that b term tells us where our graph is actually going to cross the y-axis. So from that, we know that y equals 3x minus 2 would have a y-intercept of negative 2. It's going to cross the y-axis at down 2 units at negative 2. Y equals 6x plus 7 would cross the y-axis up 7 units or at 7. And y equals 8x would actually cross the y-axis at 0. It would cross at the origin. So looking at these two, again, equations, functions, if we're asked at what point, now you got to be careful about this, at what point will this function cross the y-axis? We know that this y equals 6x plus 2 will cross it here up 2 units. I don't know where it's going to go from there yet, but we do know it's going to cross here. And if it asks you for the point where it crosses, this point is actually the point 0, 2. Same thing with the second one, y equals, or f of x equals 2.4x minus 7.1. I know that my graph is going to cross the y-axis at negative 7.1, which is the actual point 0, negative 7.1. Okay, we're next going to talk about a concept called slope. And the slope is simply the slant of a line. And it tells us how steep, I guess is another word that you could use. It's the slant of the line or how steep the line is. There are 4 basic types of slope that we're going to cover. The first type is a positive slope. Anytime that you have a line that slants uphill from left to right, that line has a positive slope. The second type of slope, and let me put positive there. The second type of slope that we're going to talk about is a negative slope. And anytime you have a negative slope, that means from left to right, it actually slants downhill, steep-wise. The third type of slope that we're going to talk about is a zero slope. And when you have a zero slope, that would be, it slants none. It doesn't have any slant from left to right, so that would be a horizontal line. And the fourth type of slope that we're going to be talking about is an undefined. Now, we got to be careful with this, because an undefined slope actually is not a function. An undefined slope is a function that, or excuse me, is a relation that looks like a vertical line. So therefore, that would definitely not be a function. But there you see the 4 types of slope: a positive slope, negative slope, zero slope, and an undefined slope. Now, if we go back to our previous example, a couple of pages ago, we see here that we had the equations y equals 2x plus 5, y equals 2x, and y equals 2x minus 5. And I noticed something about all 3 of these lines. All 3 of them have the exact same slant. A word that we used in geometry was actually parallel. These lines are parallel with each other. But since they have the same slant, looking at the equations, y equals 2x minus 5, 2x, and 2x plus 5, those three equations, something leads me to believe that since these lines are slanted the same, and since this number here is the exact same number in all three, that number must have something to do with the slant of our line. And it actually is the m in our function notation, in our equation of a linear equation here. The m actually stands for the slope. And a reminder again, the b was the y-intercept. And we actually call this form, I can go ahead and call it this now. We call this form, this f of x equals mx plus b, or y equals mx plus b, we call it slope-intercept form. For that reason, since the m is the slope, since the b is the y-intercept, then we call this form of a linear equation the slope-intercept form. Okay, next up I need to share with you how we actually find the slope. We know that if we were given y equals 2/3 x minus 6, we know where the slope is. But we need to know what the slope means, what having a slope of 2/3 actually means to us, which by the way, here the slope would be 2/3, the y-intercept would be -6. But here's your formulas for slope. Slope, which has an abbreviation, like we said, of m, I'm not sure why, but slope is equal to m is equal to the rise of a line over the run of the line. Or the line's change in x, change in y, how much the y's change over how much the x's change, the change in x. That formula could be written also as y2 minus y1 over x2 minus x1, and we'll show you more about how to use that shortly. Some books even do this, I believe yours might. Some books even say, you know what, y2 minus y1 over x2 minus x1, yeah, you can actually do, instead of y2 minus y1, you can do y1 minus y2, as long as you do x1 minus x2. You're going to get the same answer either way. So here we go. Our first method of finding slope is if you're given a line, what you need to do is pick two what's called lattice points. And the lattice points is any point where the graph crosses just exactly on an intersection of an x and y here. So here they've got a lattice point here because I noticed that it crosses at 7, 3. You see that. And here you have a lattice point at 2, 1. Okay. So if we're given a graph, one method of finding the slope, this is where we use rise over run. You take those two lattice points and you find the rise between those two lattice points. Okay, how do I get from this point to this point? How much do I go up or down? If you go up, that would be a positive rise. If you went down, that would be a negative rise. And after you rise, we're going to run. Okay, if we run to the right, that would be a positive run, and anytime we run to the left, that would be a negative run. So the slope here, notice that to get from this dot to this dot, we would rise we would rise 2 boxes, and we would run 1, 2, 3, 4, 5 boxes. If we have a rise of 2 and a run of 5, and since slope is equal to rise over run, and we rose 2 and we run 5, then I've got a slope of 2/5 here. Another way of finding slope, once again, is by using the formula y2 minus y1 over x2 minus x1. These 2's and 1's are what's called subscripts, okay? And they simply mean this. The second y minus the first y, the second x minus the first x. And notice here that we've got 2 different points. We have an x, notice those are both x's. X's are your inputs, they're always found first in your order pair, and y's are your outputs. Notice here your 1 and 3 are your y's. So the second y minus the first y. Now which one do we let be second y, first y? It really doesn't matter. Here they've kind of done it for us. They've said this is 0.2 and this is 0.1. So since this is 0.2, this must be my x2 and this must be my y2. Since this is 0.1, this must be my x1 and my y1. So let's plug into this formula, y2 minus y1. The second y minus the first y would be 3 minus 1. The second x minus the first x would be 7 minus 2. So we see here also that we have a slope of 2/5. And like I said, you can also do the first y minus the second y over the first x minus the second x But what's going to happen there is you'll get 1 minus 3, which is negative 2. 2 minus 7, which is negative 5. But we also know a negative divided by negative is a positive, so therefore we have the exact same answer. Now, your next question might be, what if I didn't choose those 2 points? What if I chose this point and let's say this point, or maybe these 2 outside points? Let's do that. If you counted rise and run, you no longer get that same 2/5. You actually get 4/10. But we see that rising 4 and running 10 is going to be, if we reduce this, the exact same thing as rising 2 and running 5. So anytime you're dealing with a linear equation, you have a constant slope. It doesn't matter which lattice points you choose, you're going to come up with the same answer. Okay, let's start trying to tie everything together now. Here I have the function y equals 2x plus 3. In previous sections, we learned that we can actually graph this function by using the table, x and y. We can plug in any x's we want to. Let's do negative 1, 0, and 1. We take out the x value in our function. We plug in negative 1 first. When you plug in negative 1, I'll do this for you, you get 1. Plug in 0, you'll get 3. And plug in 1, you'll get 5. Plotting those points, when x is negative 1, y is negative, positive 1. When x is 0, y is 3. When x is 1, we have a y value of 5. And let's see, again, we know that we can actually find slope and y-intercept by simply looking at our function, but I want to show you the relationship between these. Okay, so now here I've got the graph. Let me connect my dots so I've got a smooth function here. So there's the graph of y equals 2x plus 3, and we do know that graph continues forever in both directions. And now that I have my graph, I want to point out 2 things to you. Here's my y-axis, here's my x-axis. Notice where my graph crosses the y-axis, right here, at a value of 1, 2, 3. And reminder from a while ago, the number at the end, the number being added or subtracted, will always be your y-intercept, and that matches up. I just wanted to show you by graphing this with a table that it does match. Something else, picking any 2 points, and we can do it from the table. We'll do it both ways. We can do it from the table, or we can do it from the graph. Picking any 2 points, let's choose maybe these 2, and finding a rise and finding a run between those 2 points. I have a rise here of 4, and I have a run of 2. So my slope would be a rise of 4 and a run of 2, which when reduced gives you 2. Which we know from before also that we can find a slope by simply looking at the number in front of our x value, or our number in front of our x in our slope-intercept form of this equation. We can find that same information from here as before. Anytime you're looking for slope, slope is also equal to y2 minus y1 over x2 minus x1. And we get that exact same answer because notice here, let's let this be our second point and let this be our first point. And our second y minus our first y over our second x minus our first x yields the values 2 over 1, which again is equal to 2. So with that said, if I give you an equation now, f of x or y equals 2/3 x plus 4, and I ask you to tell me what is the slope of this line, because it is a line, it's written in linear form. What is the slope of this line and what is the y-intercept of this line? You can now tell me that the slope is simply 2/3 because it's located right in front of x, and that the y-intercept is, and be careful, let's give the point here, let's not just say 4, but the y-intercept is the point 0, 4, which is always located at the end. But once again, what if we're not in slope-intercept form? What if we have 2x plus 5y equals 10? What are we going to do with this now? Because we know that slope-intercept form looks like y equals something times x plus some other number, to where m and b are numbers. That's not in this form. Notice my y has lots of other stuff over here. Within 2 steps, we can get this into slope-intercept form. Reminder, you have 3 terms. To get it in slope-intercept form, to get y by itself, we first move our non-y term. And I'm going to write it first as I move it. I now have 5y left on the left side of the equal sign, equals. When you move a positive 2x, because that is a plus 2x, you're going to get a negative 2x on the other side. 10 is understood to be positive, so we leave it as positive on this side as well. After moving your 10, after moving your 2x, we now have to get rid of this 5. Since 5 is being multiplied by y and we want to only get rid of our 5, we're going to divide. So we're going to divide every term on the other side of the equal sign by 5. And I'm left with y equals 2 divided by 5 is going to give us a decimal. 2 divided by 5 or 2 over 5 will not reduce. So we're going to leave that as negative 2/5. Leave our x. 10 divided by 5 is divisible. 10 divided by 5 is 2. So what we've done, our equation 2x plus 5y equals 10, we've gotten it into slope-intercept form. Now that we've gotten it into slope-intercept form, we can say that our slope is negative 2/5. Let me remind you here, since our slope is a negative, what that's going to tell us about that line, and there's 4 types of slope. There was a positive slope, there was a negative slope, there was a zero slope, and there was an undefined slope. Now, since this slope is a negative number, that makes it fall into this category. We know that it would actually slant down. And not only do we know our slope is negative 2/5, but we also know that we have a y-intercept of 0, 2. I do want to caution you on one thing as far as slopes go. When you have a negative slope, like we just had, and I know that that's a downhill slope. From left to right, it should slant downhill. Anytime you have a negative slope, that negative can be placed because we have a rise and a run. Does that mean we have a negative rise or do we have a negative run? Well, starting from a point, this negative can go with the top or it can go with the bottom. It doesn't matter. It could be a negative 3 over 10 or it could be a positive 3 over negative 10. Because think about it. From a point, if you rise in a negative direction and then run in a positive direction, that's the exact same thing as rising in a positive direction and then running in a negative direction. You're going to get the same type line. You're going to get a negatively sloped line. So anytime you have a negative slope, that negative can be applied to the top of the slope, or to the rise, or it can be applied to the bottom of the slope or the run. Okay, finally, let's look at an application problem for slope. Here we have a problem about student debt. Says the average educational debt per college student at his or her graduation has steadily increased. In 1993, the average debt was $14,500, and by 2011, 4,500 in 1993, and by 2011, this amount has increased to 26,600. It says find the rate of change. And that's exactly what slope is. Slope is how slanted a line is, but not only that, slope is a rate of change. And we'll show you with this example what we mean by that. What we want to do is, in order to find a rate of change, we're going to find the slope of this line. And we find slope by using the formula y2 minus y1 over x2 minus x1. Or you can count rise and run. It's going to be harder to do that here since you have funny numbers. But our y2 minus y1, our second y minus our first y would be 26,600 minus 14,500 divided by our second x minus our first x, 2011, minus our first x is 1993. And hopefully, like I said, with this problem, you'll see a good example of what slope actually tells us. So from 26,600 to 14,500, that's a difference of 12,100. Per from 2011 to 1993. 2011 minus 1993, that's a difference of 18 years. So what that means is our debt has changed by $12,100 over 18 years. That tells you how quickly the debt is changing on average. That's the reason we call it an average rate of change. But we could go a step further. Let's reduce this. Let's take out our calculators and let's actually take 12,100 and divide it by 18. And we get about $672.22. And let's talk about what that gives us. If our debt changed $12,100 over the course of these 18 years, if we divide that debt amongst the 18 years, that's telling us that we're changing by about $672 $672.22, that many dollars per year. So that's how much we're increasing each year on average about. And since this is linear, that's exactly with this graph how much it's increasing each year. So we could actually use that slope or that rate of change to find out, well, what's the expected debt to be in 2015, 2020 by using the same graph. Okay, let's work one last application problem here. It says daily newspaper circulation has decreased in recent years. The following graph shows the circulation of daily newspaper in millions for 3 years. Find the rate of change in the circulation of the daily newspapers per year. So what we again see, we see that there is a steady decline. To find out what the rate of change is, we're doing y2 minus y1 over x2 minus x1. Our second y, and I'm going to let this be my second point and this be my first point. My second y would be 46.3 minus my first y would be 52.3 divided by my second x is 2009 and my first x is 2006. So we see as we subtract these, we went down from from 52.3 to 46.3. That's a decline of -6, and again that was in millions. So -6 million over the course of those 3 years. And again here we see that we have a negative slope, and the reason that we have a negative slope is because there is a decline. Okay, it's going down, and it's going down $6 million over 3 years, and as we reduce that, we get -2. So what that means is if it's going down -6 over the course of 3 years, then that means steadily it's went down 2 million per year. So you could actually write that as a decline of -2 million per year. That's what your slope is equal to, is -2, and we see there again what that means to us in application type problems.